So we have seen for a bimolecular reaction, the rate constant can be derived according to the transition state theory for bimolecular reaction, and that we found as if you remember that it's a bimolecular elementary reaction, something like A plus B, and the assumption was that we have a transition state in between, and that is giving the product, and then the rate constant was found using the Eyring equation was kBT by H, and then I have the ratio of the partition function of AB dagger divided by A and B. I was using probably small q notation, QA, QB, and then this has 1 degree of freedom less, that is why we wrote it as a prime, and e to the power minus E star by kBT, where E star is the differences between the 0 point energies of the reactants and the transition state. Now today we will see what are the treatments for unimolecular reaction. Now there are many reaction, unimolecular, again it is a unimolecular elementary reaction, and there are many theories to explain the unimolecular reactions, and there what is an unimolecular reaction in that sense. So basically I will have one particular species going into the product, and we are in a process to understand how one can write the rate constant for this unimolecular reaction. Now if you think that we already studied this Lindemann hypothesis, I am going to repeat here once again, so that we understand what are the drawbacks in the Lindemann model. Now Lindemann proposed that for any unimolecular reaction there is a bimolecular collision that precedes the unimolecular reaction. So that is known as Lindemann mechanism. Sometimes it is called Lindemann-Christiansen mechanism, but we will just call it as a Lindemann mechanism, or Lindemann hypothesis, or Lindemann model. So Lindemann said that for any unimolecular reaction you will have a collision of the molecule with something, some other gas molecule. This M can also be the wall of the container, and then you first form an energized molecule, and then this energized molecule subsequently gives rise to the product. Now for unimolecular reaction there are many theories. For example, there were people hypothesized initially that the radiation or the black body radiation from the wall of the container actually causes the unimolecular reactions to happen, because the question was, if a molecule is there, what is the process of activation first, because it has to cross certain energy barrier for the reaction to occur. Now one of the theories, or one of the examples of unimolecular reaction, a very nice example is cis-to-trans isomerization. Now here cis goes to trans, and depending on the system, trans can also give you back the cis isomer, and these are actually called true unimolecular reaction, in the sense that you have really one particular molecule and it is giving you the another particular molecule. In this case the molecules are isomers. Now the question is, if we have two process, so I have a bimolecular process and then which is followed by a true unimolecular process, how one can write the rate constant, and that already we have seen or in many cases. So we'll use the steady state approximation here, and using the steady state approximation for the intermediate. So the intermediate here is this energized molecule for the intermediate concentration. Then we can say that the rate of the unimolecular reaction, overall rate, that we have again derived when we discuss the reaction mechanism, and you can actually go back and have a look at those lectures. So that will be nothing but equal to K1 into K2 times A into M divided by K1, it will be K minus 1, not K1, K1 into M plus K2. So then what people figured out is that they actually plotted this unimolecular rate as a function of pressure. Now, pressure of what? You can actually think of the pressure of the second body M. Now, you can actually have inert gases also for this reaction. The M can be actually some other gas molecule, and then you study the reaction, and then experimentally people found the curve looks like something like this. So, at a very low pressure region, you can see that it is basically the rate constant itself, K unimolecular, is actually a it depends first order with respect to M, and then at a very high pressure, you will have that the apparent rate constant, which we can write it as the apparent rate constant as K effective times M. So, this is one way of writing it. I'll just write it as like this, K effective into A, where K effective is this entire term. So, K effective is nothing but K1 into K2 times M divided by K minus 1 into M plus K2. Now, the question is, this is an effective rate constant, and it will have its high pressure and low pressure limit, and then as is apparent from this equation, that if you have in the low pressure regime, so you can think that the concentration of M will be much small. So, K minus 1 into M, that term will be much smaller than K2. So, what you will have is that the effective rate constant will be something like K1 into M. So, that is the linear dependence in the low pressure regime, and in the very high pressure regime you will have the other constraint, that the K effective will now be, so basically in that case K2 is much smaller than K minus 1 into M, and then what you have is, so I will ignore this other term K2, and then the M actually cancels. So, then you will have K1 K2 by K minus 1, which is a constant, and that is why you see a flat line. So, it does not change with pressure, the total pressure. Now, again M can be A itself, M can be something else, M can become some other gas also. Now, so if it is actually some other gas or the A itself, then I can actually represent the concentration of M as just pressure. So, this x-axis is nothing but some textbook actually write it as just pressure. Now, so this is basically the unimolecular reaction kinetics at a very high and very low pressure regime. Now, you see that what is the physical significance here is that what Lindemann hypothesis says is that for any unimolecular reaction, the activation is by collision. Activation is not by some thermal black body radiation from the surrounding, because that is not good enough to actually excite a molecule close to the dissociation limit, so that some bond breaks and some rearrangement happens, and then it gives rise to the product. So, collision is necessary. And the second thing here is that whenever you have the collision, you remember that from collision theory, you can think that if the process of energization is happening, so the rate constant for energization in this case is this first step, where this forward step. So, you are having an energization, and then you are having a de-energization or deactivation, and then in the second step what you have is that the energized molecule actually give you the product. Now think about it, like if I have a small pressure, if I am working in the small pressure limit, so there a collision is happening, and I produce some ester molecules, but these ester molecules have a little chance to get deactivated by collision again. Because the number of collisions are less in the low pressure regime. So whatever collision is happening, and if the collision actually results in formation of ester, so those esters will actually give you product, and that's why you are having with increase in pressure, we are having actually an increase in the collisional activation or energization, the very first step in that equilibrium, the forward step in that equilibrium. But if I actually increase the pressure too much, then what will happen? These ester molecules will also collide among themselves and as well as with other molecules, and they get collisionally deactivated. So then the rate will actually get saturated, and because the deactivation will take part, and then you will have something like a steady state like expression, not steady state like the equilibrium approximation like step, and we discussed about it that the rate of deactivation of the you have to actually remove the intermediate very quickly, then actually you can get this steady state approximation hypothesis. So there it's a similar concept here. So here actually I am talking about in the language of deactivation, and then if K2 is much higher then the rate of actually deactivation is much higher than the rate of product formation, which will be the case for the high pressure limit. Because if you remember that the product formation does not depend on the collision, because product formation is only the second step, this step, and then in the high pressure limit the collision will happen and it will deactivate. Now the question is in this entire thing we only talked about the kinetic energy or the translational kinetic energy contribution. So molecules are colliding, and that is the entire source of activation of these energies. Now the question is there any contribution from internal degrees of freedom? So that is one of the biggest question, contribution from internal degrees of freedom. Internal degrees of freedom, by that I mean that if you consider some, say, internal vibrational degree of freedom, is it important to consider for this unimolecular reaction to happen? Secondly, this mechanism, whatever we talked, it sheds no light on how this process actually happens, how ester is going into product. That dynamics or understanding of how this thing is actually occurring, that is not known. Only thing the Lindemann hypothesis or Lindemann model provides is to tell you that how these reactions are happening, how this collisional activation is happening, how the ester molecules are formed. Now these problems were subsequently tackled by many other scientists, and many great people in the area of chemical physics actually contributed to this topic. And then they said that this entire hypothesis we can or entire theorem we can think that okay, fine, these ester molecules are getting activated, but collision can give you an energized activation. So let us first try to understand or try to write down what will be the frequencies of this collision K1 and what will be the frequencies of this deactivation. Now for deactivation you do not need any energy barrier, because it's already some energized molecules are there, and with collision they will deactivate. So I can say that this deactivation rate is nothing but the collision frequency itself. So I am writing it as Z1 in the sense that this 1 denotes that we have the collision between same type of molecules, but it's not necessary that we have to write it as Z1. And secondly, this K1 step, it will also become dependent on the number of collisions, but with a certain energy criteria. And we know that from collision theory that we can actually calculate it in the simple collision theory, that if we say that there is some threshold energy which is suppose E star, then we can say that the number of collision that is giving successful reaction is something like Z1, the total number of collision into that probability, which is nothing but a Boltzmann factor. So together I can say that in the very high pressure limit of unimolecular reaction, which we wrote it like this, and sometimes we wrote it as K infinity in the sense that the pressure is in the very high pressure limit, and that expression for this K infinity, which is the ratio of K1 by K minus 1 into K2. So that becomes something like K2 into e to the power minus E star by KBT. That's what Lindemann hypothesis is. Now then came another model which was put forward by Hinshelwood, and Hinshelwood proposed that internal degrees of freedom are also very important. Now, what is Hinshelwood's proposal is that, okay, fine, so what are these internal degrees of freedom, and how we can model these vibrations. Now, these vibrations, suppose if you have a linear molecule, already we said that there will be some 3n minus 5 degrees of vibrational freedom. For nonlinear molecule, there will be 3n minus 6 vibrational degrees of freedom, where n is the number of atoms in the molecule. Now, all these vibrational motions or all these vibrational oscillator, I mean, you can actually think that this vibrational motion are very much harmonic in nature. Now, truly, you cannot actually have any harmonic motion, because a harmonic oscillator, if you keep on putting energy, so the energy will actually keep on increasing, and if the bond behaves like an harmonic oscillator, it will never break. So in order for the bond to break, it has to be anharmonic, something like that, so that if I actually reach this much energy, I see that the potential is not actually a bound potential, and it should now break. So in this axis I am plotting the energy, and this axis I am plotting the equilibrium bond distance, and that we already discussed that if I excite I mean give this much amount of energy, that we call as D0, it's dE, sorry, and if I consider the actual energy which is calculated from the 0 point energy, that is known as D0. So that amount of energy if I put, then the bond will break. Now in a molecule, you might have many different vibrations. Of course, there are many different vibrations, and you can have actually different bonds, and one of them might be very weak, meaning in the sense that suppose the way I have drawn it, so this is for one particular bond, but another bond can be very weak, for which the actual dissociation energy which you need could be much smaller. So the idea is that when you actually energize a molecule which has many bonds or many vibrational degrees of freedom, then first the energy gets randomized among the all vibrational modes, and then the weakest bond breaks, and that will form our the starting point for the next level of theory, which is known as the RRK theory. But before that, what we are discussing right now, the Hinshelwood mechanism, that also basically provided the necessary concept for developing the RRK theorem, where Hinshelwood said that we know that this is actually an anharmonic problem, anharmonic oscillators. Every chemical bond have to break, and then it cannot be an harmonic, cannot be modeled as an harmonic oscillator, but with some approximation we can say that for the sake of calculation, because you can actually easily find out many interesting statistical properties for an harmonic oscillator. So we can actually make this harmonic approximation. And then Hinshelwood said that let us think about this problem that I have actually a fixed amount of energy, and which is stored in the ester molecule. And then the question which I am asking is that how this total energy, which is suppose have some fixed amount of energy, let me call it as say E, where E is a fixed amount of energy, how that energy is partitioned among these different modes, because when due to collision I am actually activating a molecule A star, the activation means actually that all the energy doesn't go into its translational degree of freedom, because if it goes into translational degree of freedom, nothing will happen, only the energized molecule will move at a faster speed. But in order for this A star molecule to break, this energy should be transferred or channeled to its vibrational or the internal degrees of freedom. So the question is, if I have a given amount of energy in the molecule, and how this energy is partitioned among all these 3n-5 or 3n-6 degrees of freedom. And let us call this number, or how many vibrations are present, I am just writing it as S. So I have actually S vibrational degrees of freedom. So degree of freedom, or the vibrational degrees of freedom, is S. It's actually small s, you can write it as like this, but I am writing it as like this, it's not capital S. Now, now for harmonic oscillator, you can actually talk in terms of, instead of the total energy, I can actually talk in terms of, say, what are the number of quantas. Let us say, for example, if I have 10 quanta in a particular vibration, so the total energy will be 10 plus half h bar omega, 10 plus half h nu, something like that. So suppose I have a number of quanta is, I am writing it as say V, because V is typically the symbol which you use for the harmonic oscillator, energies, the quantum number. So V plus of h bar omega, that's how you write it. So that's why I'm just writing it as V. So suppose I have total number of quanta is V, and total vibrational degrees of freedom is S. Now the question is, how many different ways I can put this V quanta in S harmonic oscillator. Now each of these harmonic oscillator has its own natural frequencies, meaning they represent some kind of bond or some combination vibration, something like we talked about water. Say for example, this, it has two bonds, but instead of visualizing it as that the bonds are vibrating locally, you can actually think about a global motion, which is known as the normal mode vibration of the entire molecule, and you talk about the symmetric and asymmetric vibrations. Now this problem you can actually solve statistically, and then you can think and it in a very interesting way. Now suppose I have, I am giving you a very simple example first. Suppose I have 5 rooms, and then I am putting some balls in these 5 rooms. Suppose I have 3 balls, and these 3 balls I am asked to put actually in these 5 different rooms. I can put it in many ways, like I can put these 3 balls like this in one particular room, because there is no such biasness that I cannot put more than one ball in one particular room, meaning I can there is no such biasness that I cannot put all the V quantas in the one particular oscillator. So this is related to something known as if you have studied this quantum statistics, this is exactly how we can derive the Bose-Einstein statistics, as opposed to the other statistics which is known as the Fermi-Dirac statistics. And so there the difference is that when you derive the Fermi-Dirac statistics, you have to actually, you can put only one ball in one of the rooms because of Pauli exclusion principle, and Fermi-Dirac statistics are obeyed by fermions, and which says that it basically comes from that antisymmetrization principle, that you cannot put more than one particle in a given state, electronic state. Now in this case we have that relaxation, we can put as many number of particles as possible in one particular room. So then ultimately the problem is very interesting. If you have say 5 rooms in this case, now look at it here, how many partitions I have? I have basically 1, 2, 3 and 4. So if I have 4 partitions and then I have 3 balls, so the problem right now is that how many different ways you are actually permuting these 3 balls and these 4 partitions, meaning the way I have written it, in this 3 and 5 way, there could be another possibility. Let me just draw it. So suppose I could actually put this thing like this and the two other balls like this. So ultimately what you are doing is you are permuting these balls, and you are also permuting the partitions. So the number of partitions you see here, if I have actually s degrees of freedom or s rooms, you can think about it. So I have actually s minus 1 partitions. So ultimately what you are left with is that you can actually have the total number of ways of having say a V quanta in S oscillators or S number of degrees of freedom or S oscillators, because these are all harmonic oscillators, is nothing but I will have the entire permutation of them. So I have total V quanta and I have S minus 1 partition. So that will be the answer. But in doing that, you are actually you can also think about it that I have say particle 1, particle 2 and particle 3 like this, but I could actually get another combination that these 2 and 3 gets exchanged. So that will have one particle in the first room, two particles in the second room, but these two particles, the arrangement can be also reversed because the way I have drawn it. But these two arrangements are identical because in this case these quantas are indistinguishable. Now this is the striking difference for the way we derive the Maxwell-Boltzmann distribution, and we are doing it right now. For quantum statistics, the particles like the fermions or the bosons, whichever you talk about, are actually indistinguishable. So they are identical particles which we did for Maxwell-Boltzmann. Here also these are identical particles. There is not two different particle statistics. All the particles are same in nature. But in Maxwell-Boltzmann distribution, those were distinguishable. I can label them as A, B, C, D. If you remember the lecture, so that's how we developed this distribution function, which we did not derive properly, and we gave some hints, and we gave we derived it in the lecture note. But here the interesting thing is that these particles. This permutation between the particles, you cannot actually take it as a new distribution because the particles are indistinguishable. So I have to divide it by the number of ways the quantas can permute among themselves, which is V factorial, and the number of ways the partitions can also arrange among themselves. That will be S minus 1 factorial. So this is the total number of ways, which means this is nothing but our degeneracy, or it's related to something like degeneracy. Again, why I am calling it as a degeneracy, because if you remember that I have given some energy, and these are the number of possibilities, which means actually each of these possibilities given corresponds to a particular microstate. So the total number of microstates, which are basically the degeneracy of that level, is given by this number. So now the question is, so how one can get the rate constant from here? So what we just said is that the probability that the V quantas are in this particular S oscillators, it will be nothing but something like this degeneracy, which we just calculated, times e to the power minus h nu and by kBt, because you know that if I have actually V quanta, the total energy will be V plus half h nu, but that half factor we are right now ignoring. We are just writing it as V into h nu. So this will be nothing but V into h nu divided by the q, and where q is nothing but the partition function which we discussed. So this is basically the probability distribution. Now this probability distribution is in quanta. You can directly convert it into the energy, because you know the relation between E and V. So if you just multiply by h nu, it will give you the probability in energy. Now in this way one can actually get an expression for the rate constant, and again I'm not going into the details. So what Hinshelwood showed is that for the deactivation process, the collisional deactivation process, you can actually find that in the high pressure limit it will be dependent on the Z, which is basically the again we are writing it in terms of the unimolecular rate constant that you remember. So this deactivation process you can actually show that will be nothing but, I'm writing the final expression, E0 by kBt raised to the power s minus 1 into e to the power minus E0 by kBt, where this E0 is basically a minimum energy that you require for the reaction to happen, or we were using actually the epsilon star notation. So either notation is fine, epsilon star by kBt, minimum energy required for reaction to happen. So this you will get for the de-energization path. Now how we get this relationship? Now basically if you remember there was a collisional activation step, and now we are writing the collisional deactivation step. This will be the collisional activation step, not the deactivation. So it is basically saying, so we made actually two level of theories. One, the simple primitive thing was K1 is nothing but the number of collisions Z1 times the e to the power minus epsilon star by kBt, but that actually takes into account only the external degrees of freedom, how many collisions are there, and what is the fraction that you are going above this threshold energy, which is E star. And then Hinshelwood said, no, actually there are also internal degrees of freedom involved, and if you take into account of all these internal degrees of freedom, you can show that this your G nu, I have already showed you like partly how one does it. So it does all these statistics, and then you get this factor, but going from here to here actually you need to apply some tricks. The original derivation, the way you do is that you take them all as a harmonic oscillator, and then actually you find the classical density of states, which actually comes from the phase space. That's why we are not showing you all the derivation here. And then you can calculate the number of the rate constant for the activation process. And again, the deactivation process, according to any theory, is simply the number of collisions. I was using the Z1 notation there. So the at the infinite pressure, the rate constant will be K2 into K1 by K minus 1. So it will be nothing but K2 into S minus 1, and you can write it in a different color. So we say that the K infinity will be, according to the Hinshelwood treatment, it will be K1 by K minus 1 into K2, which is nothing but, now you can see this Z1 factor will cancel out this factor, and what we'll be having is nothing but K2 into divided by S minus 1 factorial into E star divided by kBt raised to the power S minus 1 e to the power minus epsilon star by kBt. Now this was basically Hinshelwood treatment or Hinshelwood equation, where he basically showed the unimolecular reaction or the rate of unimolecular reaction at the very high pressure limit. Now the question that remained unanswered is number one, what are, that is the biggest question. what is the expression for K2, because as you can see that K2 is still remaining. I know the number of degrees of freedom, I can actually estimate the minimum energy requirement. KBT is a constant, but then the question is, what is K2? Now that problem was tackled first by the other group, which was basically by Oscar Rice and his postdoc Ramsperger, and independently by Castle, and that is why this theory is known as RRK model. And RRK model basically tells you an interesting way of thinking the problem. They said that, okay, fine, so it doesn't matter actually, suppose you can actually have an energized molecule, but the reaction will happen when and only when those energized molecules, I mean, suppose you put an energy total E or in our language V quanta in that molecule, and how this V quanta is partitioned, that we already have done, but RRK said that reaction probability will be non-zero if and only if out of this V quanta only certain amount of quanta is going into the reaction mode. Now what does it mean? That means actually the way we drew it earlier, if you remember. So here as you can see that I have suppose a very weak bond which will dissociate, and this energy suppose in the harmonic approximation means suppose I have to supply m quanta, because these are all harmonic ladder, and if I do not supply m quanta to this particular mode, the reaction will not happen, because the reaction involves the dissociation of the weakest bond, and that weakest bond should get the sufficient amount of quantas so that actually it reaches its dissociation threshold, and it can have actually more quanta, but it has to have the minimum m quanta. So the partitioning right now is a little bit more complicated. It is not like how the V quanta is getting distributed among the S degrees of freedom. It is basically there is one more level of complication, and you can show it like this. So I have total V quanta and total S degrees of freedom. So out of this V quanta, what I am saying is that the M quanta is going for one particular degree of freedom, which is the reactive degree of freedom, and suppose that has a frequency which we are calling as nu dagger in with the similar, we are keeping it the similar notation for the bimolecular reaction, and then all this V minus m quanta for the rest of the oscillators. And if I have one particular oscillator which I have already considered, so for all s minus 1 degrees of freedom, or s minus 1 modes, harmonic modes. So that way we have to now partition. Now that probability you can also calculate, and in this case it's a similar way. So I have basically V minus m quanta, and I have to choose one particular like I have the way we do it is that I have now this particular thing. So suppose you remove this m quanta, for this you keep it reserved for this particular degree of freedom, which has a frequency nu dagger, and all this V minus 1 quanta, how do you distribute among s minus 1 degree of freedom? Now that requires some calculation. You can ask this question, why I am writing it as s minus 1, why not as s minus 2? So because I have actually s minus 1 degrees of freedom, and considering our partition thing, it should be s minus 2, but the reason here is that it is basically a joint probability, because you have a probability of having this m quanta for this particular mode, and that will also have a probability, and that will be multiplied by this probability which you are doing, and ultimately when you do all this maths, you will get something like that the v minus 1 factorial and s minus 1 factorial, but this is basically the fraction in which actually this m quanta is going into this reactive mode, otherwise the reaction will not occur. And then you have to take the overall probability, which means what is the probability independently that this V quanta is going into S oscillator. So, what that we have already calculated. So, it is V, it will be it is V plus S minus 1 factorial, V plus S minus 1 factorial into V factorial into S minus 1 factorial. So, this denominator takes into account of all different ways that you can put this V quanta in S degrees of freedom, but in all of these cases you will not have reaction. Only in those cases you have reaction where out of this V quanta only M quanta goes into a particular mode, and that is the number. So, the ratio of the number to the total number of this thing will give you the probability for this particular process. And if you keep on working on this, and basically you can make a further approximation, like this number will be nothing but you can see here this s minus 1 factorial term that will get cancelled, and eventually you will have v minus m plus s minus 1 factorial into v factorial. So, this v factorial is coming in the numerator, and then you have v minus m factorial into v plus s minus 1 factorial. Now, you can further make approximations in the sense that if I have, let us say, the v and m. So, you are assuming that your thermal energy kBT is much higher, because that is why the it's all collisional energy. So, you have accumulated some amount of energy, and which is much higher compared to your actual it is basically available, some fraction of the thermal energy is available for that, and the amount of the quantas like V and this M are much large than the number of degrees of freedom, because if the degrees of freedom is very large compared to the available quanta, then you can see that the sum of the modes will not still be excited. So, it is a very less probable that one particular mode will get so many quantas, m quantas. If you have enough number of quantas to begin with, V and M both are much larger than S, then only this will happen, and under that limit you can see that this is V minus M plus S minus 1 factorial. So, that you can now approximate to be something like V minus this factor. We can do actually two approximations, but again this is a very under this condition only we are making this approximation, that V minus M plus S minus 1 factorial divided by V minus M factorial. So, this part that actually will go as V minus M raised to the power S minus 1. Now, how we get it? So, you can see here that how I, so suppose S minus 1 is say 3. So, in the numerator I will have V minus M plus 3, then V minus M plus 2 times V minus M plus 1, and then it will be V minus M factorial, and that will cancel with this denominator. So, I will have basically 3 terms, V minus M plus 3, V minus M plus 2, V minus M plus 1, but those again I am approximating each term as V minus M. So, it will be actually V minus M cubed. So, that is how you can approximate this term. Similarly, for this term also you can actually approximate it as V factorial by V plus S minus 1 factorial is nothing but V to the power S minus 1. Now, if I now take the ratios, this probability actually becomes, as you can see here, it's now very straightforward. It will become V minus M divided by V raised to the power S minus 1, which is nothing but 1 minus M by V raised to the power S minus 1. Now, we can actually write, instead of quanta notation, we can write that the total energy, which is fixed, is nothing but V into h nu, because we are just ignoring the 0 point energy here, and the total energy that we require, so which we have been writing as E star. Some textbooks actually write it as E0, so we will follow the old notation. E star, that is nothing but M times h nu. So then actually we can multiply this numerator and denominator by h nu and convert it into energy. It's pretty straightforward. So then we'll get it something like E star by total energy to the power S minus 1. So that will be the probability of, or the basically what is the probability that you get this, let me just write it very carefully, the notation wise. It is actually a probability, something like Hinshelwood calculated, but this probability is slightly different in the sense it says that a particular oscillator which for which the energy, the frequency is nu dagger, that actually exceeds the E star, the threshold energy, and for which E star is basically equivalent to the M quantities. That probability we calculated. Now, this is basically the probability that the ester molecules, so the difference between the earlier one, which is the Hinshelwood one, is that how the ester is, how the internal degrees of freedom is partitioned in the ester, but in RRKM they said that ester will give reaction, or the reaction probability. If I just write reaction probability, will be equal to 1 if and only if I have a certain condition that a particular mode, which is the reactive degree of freedom and which has a frequency nu dagger, that gets M quanta, and if it does not get, then the reaction probability will be 0, something like that. And that was the introduction of the concept that RRK did over Hinshelwood approximation. So, and what Hinshelwood did is basically talking about the internal degrees of freedom. That was a great advancement, thinking in terms of you were talking about only translational degrees of freedom to the internal degrees of freedom, and then you calculate the reaction probability. Now the question is, fine, so those ester will react, but then I have still a problem that, okay, fine, so the ultimately the reaction probability will be K2 times this probability, which you just calculated. It's a function of energy actually, but what is the unimolecular rate then? So at very high pressure limit, which is again dependent on energy, because we are talking about only the energy dependent rate constant. Now that that they approximated, the RRK approximated as this is basically the frequency of that mode itself. Now this is something we also did for, if you remember, we also did for the Eyring equation, where we said that I have a transition state and then it is forming reactant, and there is a one particular vibrational mode that is giving me the reaction, and then we just have to multiply it by the probability, and the probability, the way we got it is something like this. Now this is the RRK expression for the reaction rate, but usually what you measure in lab is nothing but a temperature dependent rate constant, and which you can easily get by taking the energy dependent rate constant and then calculating this probability, which is an energy function of energy, and then you say that I have to make sure that these energies are actually above ester, because otherwise this reaction will not happen, because ester is the minimum energy that you need for this reaction to happen. So because otherwise if everything is below ester, then the m quantas, there is no question that there are m quantas, there is less number of less than m quantas, and there is no chance that this one particular degree of freedom will get n quanta, because there is no m quanta to begin with. So finally if we do all this integration, again we cannot show it because it's beyond the scope of discussion. So you will get the RRK rate expression. It's a very simple rate expression. You will see that it will be something like a nu dagger into e to the power minus ester by kBt. Now what we basically found going from this collision theory, which is the Lindemann theory, to this theory is very interesting. And in the collision theory says that it is basically the number of collisions. Remember, there was K2 here, and here actually they are saying no, actually it's not the K collision theory itself. It is basically the number of vibrations, or the vibrational frequency, times the energy criteria, and that is giving you the RRK rate constant. Now the final modification was done by Rudy Marcus, and who modified this RRK theory, and that's why this theorem is called RRKM theory. Now again, RRKM theory is beyond the scope of our discussion, but what Marcus did is very interesting. I think I'll just tell you the salient features what Marcus did. And he said that okay, fine, in up to RRK you are assuming that I have an A star, and I calculate the probability such that there is a probability such that one particular degree of freedom has an energy which is more than at least equal to or more than this m quanta or ester energy, and that is giving you the reaction, that is giving you the products. But what Marcus did is Marcus assumed that there is some kind of transition state, just like a bimolecular transition state, that exists before actually ester gives you the product. So in a sense that going from RRK to RRKM, Marcus actually assumed that okay, so any unimolecular process, first you have a bimolecular collision and you produce ester. Now all the esters will not give you a reaction. Some esters where actually you have so there are actually two criteria. First thing first, you have to cross the ester energy level, and once you cross the ester energy level, second criteria which Hinshelwood which RRK said is that fine, this ester is okay, but then are you sure that out of this ester m quanta has gone into that vibrational mode? So that RRK calculated. Now those fraction they calculated. Now the question is how those fraction is giving the reaction. Then Marcus said that there is an intermediate and it's just like an activated complex. There is an intermediate complex. Again, I should not call it as an intermediate because it's a transition state. And he connected the bimolecular, the transition state theory which is developed for bimolecular reaction, bimolecular elementary reaction, to the single unimolecular elementary reaction. And he did all this calculation based on the density of state. But finally, at the end of the day, surprisingly, he calculated this rate constant, and the rate constant he found to be equal to the kBt by h, and that was so let me use the original notation that we have been using, that is q a dagger with 1 degree of freedom less divided by q a into e to the power minus ester by kBt. So that's what is the RRKM rate constant. And now you see the striking similarity with the bimolecular rate constant or the transition state theory, which actually says that we have QA into QB because that was bimolecular, and this is unimolecular, that's why you have only one species QA, and otherwise it's exactly the same thing. Now we cannot show it again because it involves a lot of understanding of the classical statistical mechanics, which is beyond the scope of discussion, and a lot of understanding of the classical phase space, because if you remember I told that this transition state theory is inherently a classical theory, because it is basically transition state corresponds to a saddle point in the coordinates in the potential energy surface, which is actually has a very precise momentum and position, which means it has to be a classical theory inherently, because if it is a quantum mechanical theory, you cannot describe a particular point in the phase space because of the uncertainty principle, and because of the commutation relationship more fundamentally. And then this RRK and RRKM theories are, particularly the RRKM theory, is also based on very much classical kind of description, where the way we have derived it, if you remember that we are writing it as a all these factors as basically summation, like I have this n quanta, we are distributing it, and we are talking about the permutation and combination. But then if you look at the probability distribution, we have been writing it as a continuous integral, and there actually they also talked about the density of state, which is a continuous function of energy, not a discrete function. So there is a difference between the original derivation and the way we showed it, but again we did not derive it fully, we just gave you a flavor. Now to summarize this part, what we said so far, we talked about the gas phase reaction dynamics, and we talked about the bimolecular reaction, we talked about the unimolecular reaction, and we showed that for a unimolecular reaction, first thing first, let us just summarize this part. So we first said that there is a hypothesis called Lindemann hypothesis, and the Lindemann hypothesis said that a bimolecular reaction, bimolecular collision precedes unimolecular reaction, and this bimolecular collision is the activation process, unimolecular reaction or unimolecular dissociation, some textbook write it. And then second, and this is basically collisional activation, and he basically said the way that A reacting with M will give you S star, and this S star will give you the product. And then came Hinshelwood, and he said that okay fine, so from here you can actually get the K infinity to be equal to K2 times e to the power minus E star by KBT. And then Hinshelwood said that for this probability it's only the collisional thing, but the internal degrees of freedom also has to be activated, otherwise the bond will not break. And then Hinshelwood found very beautiful, so he basically said that the importance of internal degrees of freedoms, and he said that okay, so the internal degrees of freedom, the internal vibrational modes has to be excited, and he talked about how this partitioning happens, and he got an formula like K infinity is nothing but K2 divided by S minus 1. We wrote it as we were describing this thing, and then I have E star divided by KBT raised to the power S minus 1 into e to the power minus E star by KBT. That was the Hinshelwood formulation. And then there was this RRK formulation, and who said no, actually fine. So Hinshelwood found how V quanta are partitioned among S oscillators, That's the question he asked. And then RRK said it is similar thing how this thing is happening with the constraint or with the criteria that a particular oscillator among this S oscillator gets m quanta, otherwise the reaction will not happen. And this particular oscillator, they said, have a frequency new dagger, and they got unimolecular reaction rate, which is very interesting, which is nothing but the frequency of that particular oscillator times e to the power minus e star by kBt. Now in Eyring equation, you remember that we took it as new dagger, but this new dagger actually eventually cancelled out. So you do not need to actually explicitly use this formula new dagger in your calculation. And then fourth thing was RRKM, and he said that a transition state exists between this S star, which are giving reaction, which has actually not only V quanta in S degrees of freedom, but also M quanta in that particular reactive degree of freedom. And those esters, when they are going undergoing reaction, they actually go via a transition state, and that gives you the product. And then Marcus found that this exactly reduces to the Eyring-like equation for which was developed for bimolecular reaction divided by QA into e to the power minus e star by kBt. So RRKM theory actually connects the bimolecular reaction dynamics with the unimolecular reaction dynamics, but these were all developed in the gas phase. So we'll give you a brief introduction on how the reactions happen in solution based on our old understanding on the transport phenomena, particularly the diffusion, which will be most important thing to discuss. Thank you.